The order of operations is basically a set of instructions that tells you which mathematical operations take precedence over others and thus should be calculated first. The aim is simple, to make sure we all get the same answer. And, when followed correctly, we do. Consider 1 plus 3 multiplied by 2. If written like this, then the correct way to read and interpret this using our accepted order of operations is 1 plus 3 lots of 2. Saying 3 lots of 2 like this hopefully clarifies that I want 3 lots of 2 calculated first and the result then added to 1, giving us 7. And this is indeed the correct way to calculate the answer. However, without knowing the agreed order in which to perform the operations, you might be tempted to add the 1 and 3, resulting in a total of 4, and then multiply this total by 2, now giving the incorrect answer of 8. If I had intended it to be done this way, then verbally it would have sounded more like this: 1 plus 3 multiplied by 2. The subtle pause indicates that the sum is required before progressing to the next calculation. Or I could have said 1 plus 3 all multiplied by 2, which makes it even clearer. So how do I make this clear in written form using mathematical notation? Simple. I use mathematical grouping symbols to show that 1 plus 3 needs to be treated as one item and thus needs to be calculated before applying any further processes. Rearranging our calculation like this, what is the correct answer now? Reading it out loud with the correct order implied, I would say 2 lots of 1 plus 3, giving the correct answer of 5. Again, using lots of, combined with the appropriate pause, makes the intended calculation clearer. If I had said 2 lots of 1 and 3, or 2 lots of the sum of 1 and 3, or the product of 2 and the sum of 1 and 3, and so on, then I'm making it clear that I intend to add the 1 and 3 first, and then multiply by the 2, giving the same answer of 8 that we achieved earlier. Once again, in written form, we need the grouping symbols to clarify this intended order of calculations. These basic examples illustrate why the mathematical order of operations was developed, basically because we can't always read the intended pauses or groupings, and different answers become possible. It's already apparent that introducing symbols to group certain calculations is one way to help clarify the order, and in fact, such groupings form step 1 of the formal mathematical order of operations, recognized and accepted worldwide. In school, you probably learnt a simple acronym or mnemonic to help you recall the correct steps to follow. There are various versions of this, depending on which country or even which state or region you were educated. The 3 most commonly used are BODMAS, BIDMAS, and PEMDAS. BODMAS stands for brackets, orders, division and multiplication from left to right, and addition and subtraction from left to right. BIDMAS is almost the same, with the I representing indices, in other words, powers. Both these forms are common in the United Kingdom and Australia and other Commonwealth nations. The P in PEMDAS stands for parentheses, being one type of bracket, as we will soon see, and the E is for exponents, being another name for indices or powers. The other slight change is that multiplication and division have been interchanged, which doesn't really matter, since they are to be performed as they occur from left to right, and before we do any additions and subtractions. Canada and New Zealand use a slight variation of this, BEMDAS, with B again meaning brackets. The number of different acronyms perfectly highlights where the confusion in interpreting the order of operations lies. It's in the first 2 steps. The brackets and orders, or powers or exponents, are really intended to include all mathematical groupings and orders, not just brackets and powers. In fact, There is a newer and more descriptive acronym circulating, GEMDAS, with the G now representing grouping, and thus covers all forms of mathematical grouping, not just the various forms of brackets. I'll stick to one of the more traditional cases, referring specifically to BODMAS from here on. The most common grouping symbols are brackets, which can take on various forms and actually have different mathematical names, although they are all often simply referred to as brackets. Square brackets, parentheses, and these are braces, more commonly known as curly brackets. Mathematicians also use this type, known as angle brackets, but it is unlikely to see them used in calculations when just simply trying to emphasize the order of operations. The advantage in using different brackets becomes obvious when we have more complex calculations like this one, with brackets nested inside other brackets. Using only parentheses, like I have here, can make it more difficult to see the matching pairs, that is, where each pair starts and ends. Color coding? We can see the matching pairs more clearly now, but using the three types of brackets, like this, helps match the pairs quite simply without color coding. In any case, you need to calculate the innermost brackets first, systematically simplifying the remaining calculation until you reach the final answer, here. If this confuses you, reach for a decent calculator. Keep in mind that, within any of these grouping symbols, the entire order of operations applies again. So for example, within a pair of brackets, not only might you have more brackets, but there could be powers which need to be evaluated before moving on to any multiplications and divisions, and then lastly, any additions and subtractions. If the power is outside a pair of brackets, then those brackets need to be calculated first, before applying the power, and so on. Remember, if things are getting complicated, reach for a calculator. Before we investigate further and discuss the intricacies that cause problems, let's complete a couple of straightforward examples following the BODMAS process. Pause the video if you'd like to try them on your own first. In this example, following BODMAS, we look for brackets first, which we do have. So we must complete this part first. 2 plus 1 is 3. When working without a calculator, it's a useful technique to rewrite the calculation each time you evaluate one or more parts of it. This helps avoid careless errors, especially if you try to do it all in one go. We now have this easier calculation, 8 divided by 4, take away 3. Continuing through the BODMAS acronym, we check for any orders. There aren't any. Next we look for divisions and multiplications, as they appear. We have a division but no multiplication, so we do the division next. 8 divided by 4 is 2. The calculation can now be simplified and rewritten as 2 take away 3. Quite obviously, we only have one step remaining, but for argument's sake, following BODMAS, having completed all divisions and multiplications, we now complete additions and subtractions as they appear. There aren't any additions, just this subtraction. So 2 take away 3 gives us the final answer of -1. This is easily verified on any decent scientific calculator. In the second example, we again have a pair of brackets, but within these brackets, we have to follow the order of operations. We see an addition and a division, and BODMAS tells us that multiplications and divisions are done before additions and subtractions. 6 divided by 3 can now be replaced by 2. Rewriting the calculation, we now have 2 plus 2 in the brackets. We still have the brackets, so we must calculate that part first, getting 4. Now we can dispense of the brackets, giving us this shorter calculation. No more brackets, so following BODMAS, we look for orders. We have 4 squared. This can be replaced by 16. And again, we can rewrite our calculation. A quick side note, advanced users could have done this at the same time as calculating the brackets earlier. noticing that it was completely separate and would not impact the following steps. Only do this if you really understand what you are doing. Now we have completed the most difficult steps, so we simply need to go through and do any divisions and multiplications in the order that they appear. 16 divided by 4 becomes just 4. Now we can do the 4 times 2, which is 8. This leads to our very last step, 25 take away 8. Our final answer is 17 as verified on this calculator. Another quick side note, we can actually swap orders of multiplications and divisions, or additions and subtractions, when there is a string of only those two operations, and provided that we maintain the operation sign that is in front of the number, applying them to the very first value in the sequence. In the first version, 16 divided by 4 gives us 4, so now we have 4 times 2, giving an answer of 8. 16 multiplied by 2 is 32, and 32 divided by 4 still gives us the answer of 8. Once again, only do this if you fully understand number properties, which I will endeavour to cover in a separate video. Such properties can be really useful when performing mental calculations, because we can select the order that makes the calculation easier, such as this one, 25 divided by 2 times 4. It's easier to do 25 times 4, giving us 100, and then divide that by 2 to get the final answer of 50. Back to the topic of this video. With a clearly defined process to follow, we would expect that the order of operations is now obvious, yet people are still achieving different results, especially with calculations like this one, specifically designed to trick people and cause debate on social media platforms. I discussed this particular example in a separate video. It's not really the order of operations that is causing the problem. It's a misunderstanding of mathematical and algebraic notation. These special notations form part of our first two steps in the order of operations. It's not just brackets and powers that form groupings and orders. Square roots, cube roots and so on are also orders, and in fact they can be expressed as powers. Expressions like these are known as radicals, and the symbol is correctly named the radical symbol. The expression under it is known as the radicand, and the small value here is actually the index or power. When there isn't a number here, then it's really just a 2, but being the smallest possible case, we don't write it. You don't really need to know all this other than recognizing that these are also orders and thus need to be calculated during the orders step. Next we have fraction notation. The fraction line, known as the vinculum, means division, but it also acts as two sets of groupings each side of the division. And if we replace the vinculum with a division sign, then we would need to place the top and bottom in their own sets of brackets, and sometimes around the entire thing. This is because the fraction usually needs to be evaluated before applying any external operations. Consider this example, 50 divided by 10 over 5. Saying it as I did, you can hopefully hear the implied grouping of 10 over 5, meaning 10 divided by 5. So we need to do this first. We end up with 50 divided by 2, giving the final answer of 25. Replacing the vinculum with a division sign, the invisible brackets are no longer optional. Without them, you won't get the correct answer, as we see now. This example highlights the sorts of problems people encounter when they rewrite or reformat calculations. There are exceptions when you understand number properties and fractions, so it's no wonder these things cause confusion for much of the general public. I remind you again, if you are in doubt, you should reach for a calculator, making sure you type it exactly as it appears. Returning to BODMAS and our list of orders, we have one last mathematical notation that often causes problems. It's the process of leaving out multiplication signs to simplify an expression. We can do this between numbers and variables, or pronumerals, which are unknown numbers, or outside brackets, like this. There are also other situations, and those of you who go on to study higher levels of maths will encounter such cases. When we do this, we are forcing a grouping, and the product involved effectively becomes one item. It's as if there are invisible brackets around them, like this. This is because the product needs to be calculated before any further calculations can be applied. You were likely taught to rewrite the multiplication sign when evaluating the expression, like this, and in many situations the written calculation is still correct. However, problems arise when the abbreviated product is part of a more complex calculation, meaning there are extra processes applied to it. Following the intended order, the correct answer is 2. But here we see what happens if we don't include our implied brackets, getting an incorrect answer of 50 instead. Here are 2 more examples. You might like to pause and try them for yourself first. In both cases, doing the brackets first, we get 3, which needs to be multiplied by 2. Simply writing in the invisible multiplication sign is fine in the first case, since the multiplication still needs to be done before the subtraction, following our BODMAS rule. So we achieve the correct answer of 6. However, in the second case, merely writing in the invisible multiplication sign, we get 12 divided by 2 times 3. And following BODMAS, we need to do the division first. This time we get 6 times 3, giving us 18, which is correct for what we have written, but incorrect for the original intended calculation. The absence of the multiplication sign forces an invisible grouping, so we could have included these extra brackets to remind us that we need to do 2 times 3 first. This gives us 6 inside the extra brackets, and then we get 12 divided by 6, giving us the now correct answer of 2. Adding any implied brackets helps clarify the correct order of the calculations that we need to follow, and will help you avoid errors by inadvertently changing the intended order as we have just demonstrated. Good calculators will do this automatically, as we see here. Let's finish the video with more challenging examples. Pause if you'd like to try them for yourself. The first is reasonably straightforward. No brackets, no orders, no divisions, but we do have a multiplication, so it must be done first, giving us 8. Now we have additions and subtractions, which we do from left to right. So 10 minus 8 is 2, and 2 plus 3 is 5. This time we do have some brackets, so we must do them first. 2 plus 3 is 5, giving us 5 squared. Now we have orders which we need to do. There are 2 of them. 10 squared is 100, and 5 squared is 25. So now we have 100 take away 4 lots of 25. We have a multiplication, so it must be done next, and 4 lots of 25 is 100. Now we have 100 take away 100, leaving us a final answer of 0. In number 3 we do have brackets, but we also have a hidden multiplication sign, implying extra brackets here. So we have 40 divided by 4 lots of 5, which is 40 divided by 20, giving us an answer of 2. In the next we again have brackets and a hidden multiplication, so I can clarify the order to follow by including the implied brackets, like this. However, inspecting the innermost brackets, I find a fraction, so I could also include brackets top and bottom. It's not vital in this example, since there aren't any extra calculations applied inside the brackets containing the fraction. We end up with 10 over 5, which then becomes 2. Since we have added in the extra brackets, we can now include the multiplication sign. Alternatively, we could have simply performed the multiplication, leading straight to this final calculation, giving the final answer of 5. Number 5 is similar, but without a hidden multiplication sign. There are implied brackets in and around the fraction as before, and we still get 10 over 5, resulting in 2. However, this time there is no forced grouping with the 4. So following BODMAS, we do 40 divided by 4 first, giving us 10, and finally, multiplying by 2, we get an answer of 20. Very different to the answer in example 4. In example 6, we have implied brackets here, 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 and here, but also here. Writing them all in should help you avoid any errors. Within the brackets we see powers. 2 squared gives 4 in both cases. Rewriting the calculation, we now complete the fraction numerator and denominator, giving us 5 over 5. Note that we could have done the 3 by 3, which equals 9, at any stage, since it appears in a separate set of brackets. Our calculation is getting much simpler. In the first bracket we get 9, and in the second we have 4 take away 1. You could simply write 3 straight away, but keeping in mind that careless errors are more likely to occur when you take shortcuts, and especially when it involves combining 2 or more calculations at once. We now have 4 times 9 in our first, remaining extra brackets, and 2 times 3 in the second set. As it turns out, the first set aren't really necessary, but the second most definitely are. 2 lots of 3 gives us 6, leading to a basic 2-step calculation, 4 times 9 divided by 6. Completing these from left to right, we have 36 divided by 6, giving us 6 as the final answer. Some of you might have noticed that doing 9 divided by 6 first, or even 4 divided by 6, still gives us the correct answer, as you see here. The intricacies of changing the order of calculations is the subject for another video. It's best to always follow BODMAS and its left to right instructions, unless you have a deep understanding of number properties and calculations. Of course, sensibly, you should opt for a calculator when in doubt.